in this example, we have a melting snowball, and its radius is given as a function of time. All right, so the radius is equal to 20 minus 0.8 t, where t is in hours. And we are also given the volume of a sphere in terms of its radius, right? 4/3 pi r cubed. That's just the standard standard formula from geometry. All right, so the first question is asking, what is the instantaneous rate of change of the volume of the snowball as a function of radius? If radius is given in centimeters, give the units of the rate of change. Okay, so we need to give its units too. So we're trying to find the instantaneous rate of change of volume with respect to radius. So we're going to find the derivative. We're going to find v prime of r, right? You could think of it as dv dr, right? Let's actually write that out. dv dr, right? We're taking the derivative of the volume with respect to radius. Okay, so when I do that, we just have 4/3 pi r cubed. So the 4/3 pi is all just a constant. So all I'm gonna do is use the power rule on r cubed, and I'm going to take 4/3 pi times 3. The 3's will cancel, and I'll be left with 4 pi r squared. Okay. Now the units are going to be, if the units of the radius are in centimeters, then the volume would be in cubic centimeters. So this is centimeters cubed per centimeter. All right. So now the centimeters cubed refers to the volume of the sphere, and then the centimeters, the other centimeters, just the centimeters, is referring to the radius. So it's the change in the volume over the change of the volume in cubic centimeters per change in radius in centimeters. All right, so that's the first part, and then we're asked to find the instantaneous rate of change of the radius of the snowball as a function of time. So we're just going to use the formula that we're given. This is r prime of t, right? Now we could also write this as dr dt. Okay, sometimes the Leibniz notation is nice because it tells you what variable you're taking the derivative with respect to, right? In the first part A, we were taking the derivative with respect to radius. Here we're taking the derivative with respect to time. Okay, so we have a different variable in this that we're taking the derivative with respect to. Now this is just a linear equation, right? So the derivative of this r function will just be a negative 0.8, so it's a constant. And the units would be in centimeters per hour, right? Because t is in hours, right? T is in hours, the radius is in centimeters, so when we take the derivative, we're going to get centimeters per hour. So, all right, let's look at the next part here. We got a couple of different things. Let's see. Let's scroll down so I have a little bit of room here. All right, now what is the instantaneous rate of change of the volume of the snowball with respect to time at t equals 0? Okay, so we're going to do something similar to what we did in example 1. We're going to look at the rates, these two rates at t equals 0. All right, so at t equals 0, so first of all, I'm going to find at t equals 0, first of all, I'm going to find the radius. The radius is just given by that equation that we have above. It's 20 minus 0.8 times t, but t is 0, right? So our initial radius at t equals 0 of the snowball is 20 centimeters. Okay. So, and I need that because the rate that I have for my volume is in terms of the radius. So I need to know what the radius is. So at r equals 20, then we have dv dr is going to be 4 pi times 20 squared. All right. So that's going to give us 1600 pi. Okay, I'm just going to leave it in terms of pi. 1600 times pi. That's the exact answer. Anything else would be a decimal approximation. So this gives us the cubic centimeters of volume per centimeter of centimeter change in radius. All right, now we're going to do the same thing for the other rate. At now the formula for the radius, or the derivative of the radius, is just it doesn't even have units, but so we're, I mean, it's a radius. The radius is in terms of time, but the derivative is just a constant. So we know from above that the dr dt is just a minus 0.8, and the units are centimeters per hour. Okay, so if we want dv let's do this. Actually, if we want, what do we want? We want the instantaneous rate of change of the volume with respect to time. Okay, so if we take this 1600 pi cubic centimeters per centimeter of radius times centimeters per hour, oops, let's put the value in there, minus 0.8 centimeters per hour, right? Just like we did above, we're just going to multiply these rates, and then what we're going to have is a change in the volume per hour. So we're going to get, what did I get? I have to take 1600 times 0.8, or negative 0.8. So it's a minus 4021 cubic centimeters per hour. Okay, and now we have the rate at which the volume is changing with time. That's our d. I'll write it over here. I started writing it before, but this is our dv dt. Okay, and notice that what we did is we took dv dr and times dr dt. Okay, we took the derivative of the rate of change of volume with respect to the radius and multiply that times the rate of change of the radius with respect to time. Okay, let's see. What does this say here? Write a function for the instantaneous rate of change of the volume of the snowball as a function of time. So let's just use an arbitrary time t. So at time t, just some arbitrary time, then r of t is, like it was given up above, 20 minus 0.8 t. Now we need r, right? Because our dv dr up above is in terms of r, right? Our rate is up here is dv dr. It's in terms of r, right? So what I'm going to do is just, again, I'm just using this arbitrary time t. Then so that means that dv, let me make that v a little better, dv dr is equal to 4 pi times the r squared, right? So, and the r squared is 20 minus 0.8 t, right? It's for some whatever value of t we choose, right? So we're basically going through the same process that we did in part C. It's just that now we're just using an arbitrary time t, okay? Now, at that time t, right, we know that dr dt, we found that up above, and it happened to be just a constant, negative 0.8, right? That's our dr dt. All right, so just like we did before, we can multiply these two rates together. We can take dv dr times dr dt, and we would get 4 pi 20 minus 0.8 t, 0.8 t squared, times a negative 0.8, and that would give us, just like it did before, it would give us the rate of change of the volume with respect to time. Okay? All right, so we've laid the groundwork for the chain rule, right? We're just multiplying rates. To get the rate of a composition of two functions, we can multiply the rates, right? Because we could have found a new function, v in terms of t, by doing, we could have written v of, let's see, we have v in terms of r, but we could write v in terms of t by doing v of r of t, right? And we could, let's see, if we did that composition, right, then we would have the volume in terms of time. So we could write that as 4/3 pi, and then r cubed, right? So but then we're going to put the r in, which is 20 minus 0.8 t and cubed, right? That's our composition, right? But now that's just a function for volume in terms of time. And now we have just found the derivative of that, okay? So we couldn't do that before, but now we know what to do. All right, let's let me go on to the next, let's see what we get at. Yeah, I'll meet you in the next video.